We're going to use Statkey to explore what happens when we have an extreme outlier in a data set. First of all, we'll go into the same data set that we have already looked at using a t-distribution, nutrition study data set with the variables kettle and smoke, and we're going into a randomization distribution this time. So remember, that's going to be under randomization tests, and we have a difference of means. Here in Statkey, under randomization hypothesis tests, I'm going to choose test for difference in means. Again, upload the file nutrition study. And choose kettle and smoke as our variables. Over here under original sample, we do see the same graphs we were just looking at under descriptive statistics. Generate a few thousand samples, and we see that we do have a pretty nicely bell-shaped randomization distribution. So I would answer yes to this first question. It does look nicely bell-shaped. Let's go ahead and find a two-sided p-value here by clicking on two-tail and typing in our sample statistic 1.694. This is what we found already. Our p-value is from these two tails, 0.035 plus 0.035. I'll generate a few more thousand samples just to see if it has stabilized. Looks like it's getting a little bigger. Okay, it looks pretty close. 0.036 plus 0.036, or simply times 2, gets us 0.072. All right, this is pretty close. We got 0.05 using a t-distribution, so it's fairly close. It's not quite close enough to make the difference between reject and fail to reject unless we went really strictly with the p-value must be less than alpha. Maybe we would fail to reject on both of these. I would say that the 0.05, you could argue either way. If you really wanted to have an absolutely strict criterion, you could just take your test statistic out to a few more decimal places and you would probably find out whether that p-value comes out a little above or a little bit below. So this is pretty good, but let's go ahead and look at another example. We're going to change the columns to alcohol and smoke. So this is alcohol use by smoke, and we're going to compare mean alcohol consumption among smokers and non-smokers. So change columns. Alcohol's a little further to the right, and back here to smoke, and generate a few thousand samples. And what do we see right away? Does this look bell-shaped? I think that's probably a pretty big no. Maybe there's two reasonable bells here, but the whole thing does not form one bell. So this is definitely not bell-shaped. It looks clearly bimodal. That is a picture-perfect bimodal distribution. And if we look back at the original sample, I mean, the title of this tutorial, of course, is a pretty big clue. But what do we think? We had large enough samples, 43 and 272, that the rule of thumb should have applied and made it reasonable for us to use a t-distribution. But if this thing doesn't look bell-shaped, that suggests that using a t-distribution is not appropriate. Well, look at this one outlier in our yes group. Our yes group is the smaller of the two, so that doesn't help. And I have an outlier at 200 where the next value down is 35, right? So typical values look like they're close to 8 or 10 here, and I have one that's out here at 200. Now, I don't know if this is measurement error, right? Or if this is honestly a person, a smoker, we're in the yes group, a smoker who consumes this large amount of alcohol. But the extreme placement of this outlier is what threw off our randomization distribution. So anytime you have such an extreme outlier, you do want to question the use of something like a t-distribution for any kind of inference that you do in this data set. So we generally want to look at our data if we have the option of looking at our data, even with rules of thumb like this one. So let's go ahead and find the p-value using a two-sided alternative hypothesis, using this randomization distribution, and using the sample statistic that we can find there also as our boundary value. So that sample statistic is x1 bar minus x2 bar equals negative 5.05. So hitting two-tail, and I'm going to overwrite the negative value because that one is closer to my sample statistic. And it looks like my p-value, strangely close to the one that we just found, but that is coincidence. Let's go with 0.04 plus 0.04. I just generated a few more samples and it bumped up a bit. So 0.04 times 2 gets me a p-value of 0.08. That would still get me some level of statistical significance. We're still significant at the 0.1 level. It's not a very strong association, or at least there's not very strong evidence, I should say, of an association, but there is some evidence. But let's compare this to what we would get using a t-distribution. We would want to do a t-statistic calculation, and remember that negative 5.05 was the sample statistic that I just used. I'm going to just use this given standard error estimate here. So 4.7617. This gets me a t-statistic of negative 1.06. Now that's not very far from the mean, right? One standard deviation away. If we go into Statkey again now and go to a t-distribution, and we'll assume we're still using 42 degrees of freedom, two-tail, and overwrite this with my 1.06, I can see I get a fairly large p-value, 0.148 plus 0.148, or 0.148 times 2 gets me almost 0.3. This is about 0.296. These are not at all close. And they shouldn't be, right? This distribution didn't look at all reasonable to approximate with a t-distribution. And so if we do it anyway, we get something that's not valid. They are not close. And in a situation like this, we would trust the randomization distribution, not the t-distribution. So the randomization distribution is correct if we can see from that randomization distribution that it was not appropriate to use a t-distribution to describe the shape. So that 0.08 is more trustworthy than the 0.296. So what this tells us about that rule of thumb is that it really is just that. It's not an absolute rule. If we have the opportunity to look at our data and we can see an extreme outlier, something like a rule of thumb we should throw out. We can look at our data. If we see a fair amount of skew but no extreme outliers, then we go ahead and trust our rule of thumb. If we don't have the opportunity of looking at our data, say on a test or a homework question where all you're given are the summary statistics, then we can use the rule of thumb because we don't have much choice, right? So we should look at our sample, see if we have extreme outliers. Another thing that's reasonable to do is just generate a randomization distribution if you're not sure. If it looks approximately bell-shaped, it's okay to go ahead with the t-distribution to calculate your p-value. So keep in mind that this is an option. You would use a randomization distribution if the context were a hypothesis test. You would want to use a bootstrap distribution if the context were a confidence interval. It's still the same thing that we're concerned about, and it's the same basic criteria for determining whether it's reasonable to use a t-distribution for inference.